Okay, then let's start. Okay, good morning. Thank you so much for being here. Ladies and gentlemen, welcome to this captivating webinar on solid-state batteries. We are thrilled to have all of you here today, including our estimated industry experts, researchers, and enthusiasts from across the globe. So as you know, solid-state batteries are a game-changing innovation in our rapidly evolving technological landscape. Today, we aim to explore together the latest advancement and challenges in lithium metal production. So in the next 2 hours, we have an exceptional lineup. Yeah, tell me.
Sorry to interrupt. There is a problem with the sharing of screen. Some people is not seeing the screen, but I can see it. So, yeah.
Oh,
Yes, I can also see it.
I'm not sure. Yeah, still, maybe it's still loading for some people. Okay.
Yeah, probably.
So people say I can see it. Maybe just sorry for the interruption.
No, it's okay. Just I'm not seeing the comments passing by, so that's why.
Okay, perfect. So I think people say they can see and hear it well now. So I think now we are okay
Yeah,
to
it's a
go.
problem of loading. Okay,
Sorry.
so yeah, it's okay. So in the next 2 hours, we will have an exceptional lineup of well-known speakers who will share their expertise from fundamental principles to practical applications. So let's dive together into the presentation of into the agenda of this webinar of today. So we will start with a welcoming session by the founders of the Solid4B cluster. Then we will give the floor to the speakers to present the different lithium metal production techniques used in their projects. So to make it more interactive, we will have a roundtable session where the audience can interact with our speakers and ask their questions. So I really encourage all of you to actively participate and ask your questions in the chat. Then you can engage with our speakers. So before going further with the presentations, please allow me to present or to introduce you the founders of the Solid4B cluster, Andrea Martinez, a cell design engineer, and myself, Taco Benissa, a project manager, both work in an IBE. So Andrea and I, as coordinators of the SpinMate project, we started this initiative last October. And today, through this webinar, we are celebrating our first achievement. So thank you, Andrea, for your great job. So for those who don't know about ABE, here we are giving some information about ABE. So ABE is an engineering company specializing in battery and energy technology for automotive and stationary applications. We are partners in more than 15 European projects, and we are the coordinators of the SpinMate and Advagem project, which are a partner of this cluster. So before giving the floor to to the presenters, I want to thank all the people behind those projects involved in this Solid4B cluster, and the special thank for the SpinMate project, the leader of this cluster. Also, I want to thank Innova team for their work behind this scene. Thank you so much, guys, and for your assistance and help. So now I think before giving the floor to Timothée and to start his presentation, please allow me to introduce Timothée. He is an association officer working particularly on the follow-up of project and reporting duties at BIPA. And he will be joining to present the BAT4U, which is a partnership between the European Commission and BIPA, and he will be moderating the last session of this webinar. So, Timothée, the floor is yours. I will stop my sharing.
Hello, good morning. Can you see and hear me?
Yes, we can see and hear you.
Yes.
Okay, I still can't share my presentation.
Try it now, please.
Okay, yeah, it's fine now. Okay. All right, so I trust you can see now my screen and myself. So good morning, everyone.
Yes.
Thank you so much, Takwa, for introducing me and for inviting me to speak today at Solid4B's first webinar. It's quite an honor, and I will be presenting, as you said, the Bat4U partnership and BEPA, what we do, how we foster battery research and innovation in Europe, and also how we then support it. So first of all, what is the Bat4U partnership? So the Bat4U partnership is a Horizon Europe partnership created by the European Commission in order to help the commission. So Bat4U is a partnership between the Commission and BEPA, BEPA being the association representing the research and industry stakeholders and other stakeholders of the battery sector in Europe, especially focused on research and innovation. And with the European Commission through the Bat4U partnership, BEPA helps with its different battery experts, helps the European Commission in writing the Battery Horizon Europe calls for projects. There is a total of 925 million euro budget for the Bat4U partnership throughout the Horizon Europe program. So from 2021 till 2027. And with these 925 million invested in battery research and innovation, we decide on the topics which give birth to the new research projects. So our goal is to establish, our different goals are to establish the best innovation ecosystem for batteries in the world in Europe by 2030, to have this a competitive, sustainable, and circular European battery value chain, and also drive a transformation towards a carbon neutral society, and of course reach the objectives of the European Green Deal, of the EU Green Deal. So the way we do this is we cover the entire battery value chain within our calls. Here you can see which parts of the value chain we are acting on, and the darker the color, the green color is on the arrow, the more involved we are in this aspect of the value chain. So you see it goes really from the raw materials till the end of life and the recycling, going through advanced materials, advanced cells and packs and modules, and assembly of a battery, and of course the applications and integrations part, whether it be on mobility or stationary applications. So the way we work as BEPA and as a Bat4U partnership is through working groups, which represent different parts of the value chain. And in these working groups, our experts are involved in these working groups, have a chance to define and draft the topics for calls in Horizon Europe work programs on batteries. Of course, update the strategic research and innovation agenda of the Bat4U partnership, which summarizes the key research priorities for the battery sector and sets out and outlines the activities of the Bat4U partnership throughout the years. Of course, being part of BEPA and being part of the Bat4U partnership means that you have a first-hand information on the strategic research and innovation strategies and priorities in Europe. You already know in advance what topics are going to be funded by the European Union, and can already be part of a great network and ecosystem, allowing you to find partners for projects more easily. And of course, you get access to impactful research findings through the network as well, and through the ongoing projects, and learning from also ongoing and finished projects. I'm happy to be here as well, because in this Solid4B cluster being presented today, we have 6 projects that come from a calls for project which have been written by the Bat4U partnership. And as you see here, Advagen, Posilion, Solid, Spinmate, Seatbelts, and Amphobat come from the budget of or have been funded by the budget of Bat4U partnership, and were funded by these calls which we assisted the European Commission in writing. So very happy to support and also be present to for this session today. that's also why it's important for us to be here. I wanted to also look at future projects related to solid state, future calls for projects related to solid state batteries. You see here in 2023, in September, there is a call for advanced materials and cells development, enabling large-scale production of Generation 4 solid-state batteries for mobility applications. We of course invite you to submit a proposal to this call if you're interested in these activities, and hopefully today you can also find potential partners to join in this venture with. And in 2024 there will be another call on sustainable high throughput production processes for stable lithium metal anodes for next generation batteries, which is of course very in line with the subject covered today in this webinar. And of course, participating, if you join BEPA, you can participate in our working groups. And if you're interested in solid state batteries, working group 3 on advanced materials and working group 4 on cell design and manufacturing would be interesting for you. So I explained that we help in the creation of a project through the drafting of the calls and the funding of the projects through the BAT4U budget. But as BEPA, and so as the association, we also want to support the projects that have started and that are ongoing, especially the ones funded by the BAT4U partnership. And so we support with several things. First of all, with communication dissemination. So this fits into also my role as being here in disseminating in events and helping with events for the projects, but also communicating on the different achievements and developments of your projects. Offer a broader platform to share results, the BEPA working groups, different social media and events. Sorry, I will drink a little bit. And of course, offer our network to amplify these messages and amplify the reach of the project's results. We also want to support with clustering with other projects, of course, identifying potential projects that you could collaborate with, and that our different projects can collaborate together. Of course, here I'm happy to see that Solid4B is the projects within are already undertaking clustering activities and having common webinars. That is the kind of activities and the kind of initiatives that we are interested in supporting and in seeing within BEPA. And so I totally encourage these activities in the future as well. And also, we want to support the innovation uptake of promising project results, especially because this is something that the Commission also wants to push on, is that when positive results have been found, have been researched through these projects, we want them to contribute to society either by going to the markets and being industrialized at a large scale in order to have the greatest impact possible, and also make a sustainable and a competitive value chain in Europe. So we have different events, BEPA events throughout the year. Our first and foremost event, I would say most important, is the Battery Innovation Days, which will take place this year on the 14th and 15th of November, 2023. And that's where we spark conversations on the latest developments in the European R&I battery sector. It is organized by BEPA, Batteries Europe, and Battery 2030 Plus, and the first and second battery IPCAIs as well. So we hope to see you there this year. It will be in Bordeaux, France, and also online for those who cannot go to Bordeaux. And it's a great networking event, and I hope to see a lot of you there. We also have matchmaking events throughout the year. We do some matchmaking events for Horizon Europe calls, so that potential partners can find each other and work together on submitting proposals and creating a project. We also have networking events with battery stakeholders to find so that's the matchmaking, and also clustering events to bring projects together. This is something we are planning and that we want to do for the next year in 2024 is a clustering event focused on very ongoing projects, focused on the science, on scientific sessions and different sessions that can help projects disseminate or share the projects in a broader manner. And some thematic workshops. We also have some workshops with other partnerships, such as the 2.0 partnership, the Waterboard partnership. Mobility applications partnerships are some that we collaborate a lot with. And also workshops on innovation uptake could also be about intellectual property management, business development coaching, and so on, which could be also helpful for the projects in the future. To join BEPA, you can go directly on our website. The website will be at the end of my presentation, and in the members page, how to become a member. You have here the fees, you simply need to have some battery RNI activities within Europe to join and pay a membership fee, and those are the only real conditions to join, and we'd be happy to have you join the association to join the work on the programmation of battery research and innovation within Europe and with a European Union budget. And that will be, so here you have a small ID, but I will not delve too much into this. I will stop here. Thank you very much again for letting me present today Taqwa and the Solid4B cluster in general. I will leave it to the rest for the rest of the webinar, and I will come back at the end to monitor the roundtable. Thank you so much.
Thank you very much, Timothy, and for the nice introduction of BEPA and BAT for EU. So I think now we can move to our next speaker, Joaquin Ricarte. He's an associate researcher at CIC Energigune, and he will give us today an overview on the different lithium metal anode production methods. And he's here representing the Advagen project. So Joaquin, please, are you able to share your screen?
I will try. Can you see the screen now?
Yes,
Hopefully, yes.
perfect. Full screen, maybe? Yeah.
Yes, just a second. That should be okay, is it?
Yes, it is.
Okay, excellent. Okay, so morning everyone. Thank you, Andrea, for the introduction. So yeah, as Andrea said, my name is Joaquin Ricarte from CIC Energigune. Energigune is a research center focused on energy storage located in the Basque Country, and we participate in several of the projects or consortiums from this cluster. But today I'm here on behalf of Advagen project, which is a project developing solid-state batteries based on hybrid sulfide and oxide solid electrolyte. And from CIC, we participate in several activities, principally on the material development part, and Grazia Cardo is from CIC leading these activities, and I just wanted to acknowledge the great job she's doing. So moving on to the topic we have today for discussion, as Andrea said, I will be just giving a short introduction to the different methods with which lithium can be produced based on the bibliography. But to start with, why are we focusing on lithium metal anode? To introduce the importance of the topic, most probably you all know why we are focusing on this. Is because lithium metal anode as negative electrode shows the very high capacity and the lowest electrochemical potential, which traduces in a very high energy density and a specific energy, which is one of the goals when we develop new battery technologies. Of course, there are challenges that we are trying to address. Those are related in terms of the performance to the low efficiency of lithium metal anodes, and there is also safety concerns. And obviously, the cost is always going to be an important matter when trying to develop a new battery technology. There are many companies on the process of trying to commercialize solid-state batteries and other battery technologies based on lithium metal anode, and those that are on the screen down there, and so many others. And the strategies that, if you check the bibliography or the research that is being performed, that are the strategies that are used to address these limitations of the lithium anodes, could be divided in those four that are in this table. On the one hand, stabilizing the interface by an artificial SEI before assembling the cells. We can stabilize also the interface by the development of new electrolytes. The cycling setup and protocol is going to be important as well, of course. By cycling setup and protocol, I mean the cell format or the pressure, of course, the temperature, the current protocol that do apply. And there are also strategies in the direction of current collector engineering and the use of 3D collectors or hosts, maybe more directed towards anode-less technology. But all these strategies, I mean, for these strategies, you can find a lot of bibliography and a lot of works and publications. But something that you don't find that often is the importance of the starting material, right? The quality of the starting material is sometimes overlooked. And depending on the quality of the process, on the method that can be used for producing this lithium metal anode, the properties can vary, and this will have an impact on the dimensions that can be achieved, the thickness of the layer, and of course the surface morphology, surface chemistry, and others. So it is a really important topic. And how are currently produced lithium metal anodes? Well, the standard process, the standard industrial process, is the extrusion and rolling of the lithium. But there are other alternative methods in bibliography, which we could divide in different groups based on vapor-based, liquid-based, and electrode deposition. Even anode-less we could consider. So, and as I said, I'm gonna quickly introduce their main properties. So, as a starting point, and then we will have some other discussions in different of these techniques. So if we start with the standard industrial process, the lithium foils are produced by extrusion and rolling, but to do that, you need to get lithium metal, which is not present in the earth crust naturally. Lithium is present either in other phases in the form of spodumene pegmatites, rocks which are mined, or in brines. These ones mainly in South America, the rocks is mainly in Australia. You can see a map with the distribution geographically of the different sort of ways in which lithium is in nature. And with either of these two sources of lithium, the first thing is to produce lithium carbonate, which would then be transformed by a further treatment into lithium metal ingots. And then from there is where the extrusion of the lithium metal ingot is performed. And then if we want thinner layers, then it is rolled and lithium foil is produced. Apart from the sustainability of the process and some other concerns, limitations of this technique would be in terms of the dimensions of the foil that can be produced, and also the thickness. Traditionally, it's been about 100 microns, I would say, for extrusion, and then rolling down to 50 microns. Although we have some interesting presentation later on from one of the partners, which they are pushing beyond those limits. So we have some alternative methods, I said, to produce lithium with different properties and maybe overcome some of these limitations. If we start with the vapor phase, here we will have the PVD techniques. There are different PVD techniques that could theoretically be used to deposit lithium. The most common one is maybe thermal evaporation. There are micro batteries, solid state micro batteries, which are commercial and produced by PVD, and the lithium is in general produced by thermal evaporation. But there are other techniques like laser deposition, which have also been demonstrating, and we do have two presentations, I believe, with each of these techniques. So I won't enter into details, but the strengths of PVD techniques in general to produce lithium layers would be the purity of the lithium that you can achieve. So these are performing high vacuum, so it doesn't react with other gases or components. Then the morphology and homogeneity, you get different morphology from extrusion and rolling, totally different, and pretty good homogeneity, and you have certain control of the surface morphology with the technique, controlling the deposition conditions. And one of the main advantages as well is the very good control of the thickness that you have and the possibility of going to thinner layers from nanometers to tens of microns, I would say, or 20 microns or so. The main limitation says the need of high vacuum systems, so maybe a bit more complex method compared to others. If we move to the liquid phase, here we have some examples as well. One of them is this melting technique that has been studied for some years now by a group, Professor Stephen Kaskell's group. As I said, it's a really simple technique, no complex system required. Just melting the lithium and coating a current collector with it. What they've seen and they've published is that you need to make the copper surface lithophilic to be able to coat the surface homogeneously with the lithium, and they've managed to do this with a thin copper oxide layer on top of the copper foil. The control of the thickness and surface morphology compared to the previous one, for instance, I would say is not as good. And if we are thinking on scaling this up as lithium would be in a melted state, maybe it has to be in an argon atmosphere to make sure the safety controls are met. So that could be a complication in terms of a scale up. Another interesting method that we could include in the liquid phase is this presented by Livent some years ago and patented based on a patent they have. And the most interesting part of this technique is that they based it on the current process that is used for producing electrodes in lithium-ion batteries. So it is done just by the slurry method. So you produce slurry starting from lithium powder and then coat the current collector with it, as you can see in these pictures. And the lithium that you obtain in the foil apparently is pretty similar, as you can see in the bottom left image, similar to extrusion pre-rolling or laminating. Of course, the question mark here would be on the quality. Is it going to be better than extruded and rolled foil or not? And also working with lithium powder from the safety point of view is not ideal, I believe. And then if we move on to an additional alternative method, we would have the electrode deposition. The electrode deposition is having an electrolyte with two electrodes, the substrate where you want to deposit the lithium, and then a lithium electrode, for instance, and a power supply. So it's a method that is industrially used for other metal coatings, so it should be easily scalable and industrialized. And it's been reported to obtain really homogeneous surface and would also have a good control of the thickness and morphology. Here, the controlling very well the current densities that are used and the electrolyte composition and the additives play an important role as well. For instance, water traces have been demonstrated to be beneficial if you control them properly. Surprisingly, this would be counterintuitive, but the water traces can help if they are present in a controlled manner to form a lithium fluoride layer, and that helps for the homogeneous growth of the lithium on the current collector. And another very interesting approach that has been reported and patented is actually using lithium carbonate instead of lithium metal as a starting material and make a solution, water-based solution with the lithium carbonate, and then have a membrane through which the lithium ions are going and then produce these electrode deposited lithium foils. So here you would be avoiding the metallic lithium as a starting material. So there would be no need to produce those lithium ingots or lithium metal as a starting material, which would be a high benefits in terms of scalability if this is demonstrated in a large scale process. And finally, to finish with, another form of electrode deposition, we could see anode-less as an in situ sort of production of lithium metal. This would only be possible for those lithium metal battery technologies in which the cathode already contains the lithium, and this would mean having a zero excess of lithium on the anode, right, or on the cell in general. So it requires a very high Coulombic efficiencies, which are still to be achieved. But if achieved, this would mean having the highest energy density possible, safer because you are reducing also the amount of lithium you have on the system, and much better from the point of view of cost and processing, also sustainability. So it would be the ideal case scenario for these cell technologies. There are different strategies being addressed to make this cell technology possible. They are similar, as you can see there in the table at the bottom, to those for lithium. But in general, and as a summary to finish with, we have a current state-of-the-art conventional method, which is extrusion and rolling, but there are publication and patents related to alternative methods, and even some companies that are trying to commercialize these alternative lithiums produced by alternative methods. And it's, I believe, an interesting topic that we will further discuss in the coming presentations. There are some colleagues that will be presenting some of these alternative methods that I've been quickly summarizing. So with that, I wanted to finish. Well, most of the information I presented today is coming from a review that we published recently. So I wanted to thank all the colleagues involved in that work, and also, of course, thank to Advagen project in general, and in particular to Tagwa and Andrea to give me the opportunity to present this work today here. And yeah, if anyone has any question, I'd be happy to answer.
Thank you very much, Joaquin. Yes, I think there is some questions already in the Q&A, so maybe I can read some of them and let's see. So there is one question asking you, what are the optimum thicknesses for the lithium films to achieve the figures of merit for the batteries? Can your batteries be made flexible, batteries on PA substrates? Can you comment on that?
Sure. There's several questions in one, I believe. So the thickness, well, optimal thickness, as I was explaining in the last slide, if you have the lithium that you need on the cathode, which is the situation in the lithium-ion batteries, for instance, or for the cathodes that you use in lithium-ion batteries, these intercalation cathodes, then if you achieve a completely efficient cell, 100% or really close Coulombic efficiency, then you don't need any excess of lithium. So having zero excess of lithium in the negative electrode, that would be the ideal case. Then if you have some inefficiencies, you can have some excess on the anode side. The less you have, if you make it work, the better. You can also, obviously, you change also the surface chemistry and morphology. So maybe having some lithium layer can help for the performance of the battery. But if with those kind of positive electrodes, the less, the better. Now you have other technologies in which you rely on the lithium as a active material, like for instance, lithium sulfur. In that case, you would need at least enough lithium on the anode side to be able to, I mean, the amount would depend on the loading of your cathode. You need to pair an anode with a loading which is at least equivalent to the loading you have of sulfur on the cathode. So it will depend on the technology, of course. Then the flexibility. Well, the flexibility of the layers, again, it will depend on the quality of the layer and the method with which you deposit will have an impact. The thinner, the better for it to be flexible. But based on the properties of the lithium, the flexibility, I mean, it's really malleable metal. So it's not like other materials that would really crack, right? And about the depositing on was it in polymeric layers or?
PI substrates.
Well, depending on the method you use, you could deposit directly on the substrate. For instance, with PVD, if the material is compatible with a high vacuum and with some temperature, it would be possible with electrode deposition, for instance. Is an electrode what you need. So you need it to be metallic to be able to deposit, right? So it depends on the method you use.
Perfect. So I see there is quite some questions, but maybe we can, for the time, we can proceed for the next presenter, and we, in the roundtable, maybe Timothy can go back on all these questions from the attendees, as we will have a bit more time. So thank you very much, Joaquin, again, for
Thanks.
the nice presentation and the overview. And I would suggest now to move to our next speaker. So we have now Maria. She's representing the Hidden Project, and she's a principal scientist at VTT Technical Research Center of Finland. And she will be speaking today about self-healing methods for the lithium metal electrode. So please, Maria.
Yes, thank you. I think you can hear me and probably see my slides as well.
Yes, perfect.
Great, thank you. Thank you for the invitation to present our project here. And let's start. So indeed, I come from VTT, Finland, and I will today present the Hidden Project. And this is a bit different from the others since this has been running already for some time. It's part of the H2020 program, and the project will end in the end of next February. So we are now in the final year of the project. But as we are working with lithium metal anodes or lithium metal batteries in the project, I think it fits very nicely into this cluster. Okay, so the Hidden Project belongs to the Battery 2030 Plus initiative, which is led from Uppsala, Sweden, and it's one of the 2 self-healing projects that is under this umbrella, and then there were 3 sensing projects as well, and one project called BigMap, which is about modeling activities. And here are the project partners. So VTT is the coordinator. Then we have CNRS and University Grenoble-Alpes from France, and also Specific Polymers is from France. Then we have 3 partners from Switzerland, so CSCM, Belenos, and Bernd Fachhochschule. And then Talos from Cyprus is our dissemination and exploitation manager. And today I will first give a short introduction to lithium metal batteries, which I think most of you are familiar with already. And then so a few general methods to increase their lifetime. And then I will go into the self-healing methods, which is the topic of the Hidden Project, and let you know how we are approaching this challenge. Okay, so first of all, a picture of the lithium metal battery. So I guess we are familiar with the benefits. So we can increase the energy density by replacing the graphite anode with the lithium metal one. And of course, there are some challenges still to be solved. We have the dendrite growth, and then also the dead lithium formation during cycling. And then there are some loss of contact or voids at the interface during cycling. And these are all the things that we are trying to avoid now with the self-healing methods that we are developing in the Hidden Project. But first of all, I would like to give a brief introduction to the passive or general methods to increase the lifetime. So these are not yet self-healing methods, but other types of approaches to increase the lifetime. So we can control the lithium nucleation at the anode side by having alloys of lithium, 3D structures, lithophilic layers there. Then one possible option is to have an artificial solids electrolyte interface, which is something we are developing in the Solid project as well. Then we can have single ion electrolytes or increased lithium transference number, which should also prevent the dendrites from growing. it's also possible to have liquid crystal electrolytes. So these are ordered materials, and they will control the flow of lithium ions so that they will deposit smoothly on the electrode and not form the dendrites. And then, of course, we can increase the pressure in the cell up to a certain amount, which is still practical. Here are a couple of papers you can read for more information about those. But then to the self-healing. So what is actually self-healing? So self-healing includes always some kind of a feedback loop. And there are like roughly 2 different self-healing methods available in batteries. So one is the preventive or autonomous self-healing, which is shown here on the left side. And then the other one is the curative or triggered self-healing method shown on the right side. So if you think self-healing like in comparison to people, this preventive or autonomous self-healing can be like that you are trying to exercise and eat healthy so that you have a longer lifetime. And this same thing happens in the batteries. But since there is always this kind of a feedback loop, it could be like, okay, now I feel a bit tired, so I try to sleep more next night. And then hopefully this will increase the lifetime of the battery. And then the other one is this curative approach. So then you first really need to detect that something is wrong. Battery is degrading. You need to have some sensors in the battery to see that now something is going wrong. Or then if thinking about people, you can like measure that, okay, now I have fever, I need to take some medicine. So it's really something that you first analyze and then trigger the curing in the battery. And then you can recover the performance to the hopefully close to the original state of health. And I added here also this recycling bubble as like, I think recycling could be considered as an extreme case of curative self-healing, even though it's not really considered to be that, but that's like just like an example that if we tear everything apart and build a new battery, that's kind of the most extreme self-healing method that we can use. So what kind of self-healing methods for lithium metal batteries there then are? So most of them that have been presented in literature are these kind of preventive or autonomous methods. We can, for example, have a self-healing artificial solid electrolyte interface. So this means that when there are volume changes in the lithium metal and lithium electrode thickness varies during cycling, then the cell layer on top of it can cope with these volume changes. And if it cracks, then it can heal again. So there's like, for example, dynamic hydrogen bonds that will attach if there is a crack. We can also have self-healing separators. It can be a piezoelectric material. So piezoelectric material is such that if it bends, then there will be automatically an electric field formed in the position where it's bending. So this will create a local electric field and then guide the flow of lithium ions to land between the dendrites and not on top of them. We can also have self-healing electrolytes. So if there is a crack forming in the electrolyte, for example, in a ceramic rigid electrolyte, there can be some self-healing materials embedded in the system so that they will heal this crack if it is formed. And then, as we know, the dendrites can grow along the cracks. So if this crack is then covered and healed, then we can prevent the dendrite growth. There are very few curative methods presented for lithium metal batteries in literature. One of them is this paper in Nature a couple of years ago. where they had current pulses to reactivate the dead lithium in the cell. And it showed that we can activate the dead lithium and recover the performance a bit. But I think there is still some work to do to upscale it, since this was done in coin cells. And we actually tried this in the hidden project, even though it was not originally planned in the proposal, but we wanted to test this in the pouch cells. And we actually saw that it seems that we can have a more shiny layer of lithium after these current pulses in postmortem studies, but it seemed to consume the electrolyte too much. So even though we could reactivate it, the battery died since we lost the electrolyte from the system. So it still needs, at least based on the test that we made, some more work to upscale this method. But anyway, a very promising method. Okay, but then to the hidden project. So what we are then doing, we have there two different self-healing methods. So first one is the thermotropic ionic liquid crystal called TILC, and the second one is the piezoelectric separator. We chose to develop these two methods in the project. And this is first the liquid crystal electrolyte approach. So it has like two different self-healing methods. First one is that liquid crystals are these ordered materials. They will guide the flow of lithium ions, so they can act as a preventive method to avoid the dendrites even from growing that much. And we also took another step further from this and are now heating the electrolyte. So when we heat the electrolyte above this phase transition temperature from the liquid crystal to fully isotropic material and a liquid material, we can kind of refresh the interface between the electrolyte and the lithium metal. So this part. So if there was some loss of contact or void formation when we heat the electrolyte above the melting temperature, then we can refresh the interface. And originally we also thought that we could break the dendrites if there is any dendrite formation, and we could like snap them and cure the battery that way, but maybe that was not the optimal idea, since then we would have the dead lithium floating in the electrolyte, which is not good either. But I think this like guiding the lithium ion flow and the refreshing the interface to get better contact after cycling, these are very promising methods. And we are heating it with a printed heating element on the pouch shell. And again, we are trying to upscale this from coin cell level to pouch shell level. And we have seen some kind of a preliminary proof of concept in coin cells that it works. So we can recover the performance after a few cycles with this heating cycle. But our challenge still is that we have a pretty low ionic conductivity for the electrolyte. So we can measure like 10 to the minus 4 Siemens per centimeter at 80 degrees, which is not yet optimal for the battery operation. But we could somehow at least live with this value, but actually we need to use a separator in the cell, since when this comes liquid, there will be a short circuit without the separator. So we have noticed that the separator will even more disturb this conductivity value. So we are now at the moment trying to find a spacer that could be used in the battery instead of the separator, and then also synthesizing new molecules which should originally have a higher conductivity. And here is the processing method. So we are using like a melt infiltration process. So again, if we heat the material, it can be infiltrated into the cathode as well. And the second method, as mentioned, is this piezoelectric separator. And this one we have upscaled to pilot scale already. And we use the VTD's pilot coating and printing lines to make the separator. It's a PVDF material, a piezoelectric material. And then we built pouches from it in Switzerland. And we have seen like 5 to 50% increase in lifetime with this method. But the results are still a bit inconsistent. So we need to still make more samples to really understand all the small details of the process which is affecting the properties. So, but anyway, this seems to be working and upscalable as well, which is nice. So as a conclusion, there are indeed several methods presented to increase the lifetime of lithium metal batteries. Many of them are passive, and only very few self-healing methods are presented. And most of the self-healing methods, they are preventive methods, and this kind of curative methods are very few. I think almost all of them have been presented only in small scale, like in coin cells. So there is still a lot of work to do to upscale these into the pilot level. But anyway, seems to be promising, and it remains to be seen which of the methods are proven to be most powerful. Okay, so this was all, and you can follow our project from the Twitter and LinkedIn accounts on our website as well. And I have also my own blog if you want to follow other types of activities we are working with at VDD. Okay, great. Thank you.
Thank you very much, Maria. Maybe we can have one question for you from the chat. So let's see. There is one asking, you remove the dendrites by applying the temperature, which leads to dead lithium formation. How much excess lithium are you using? And do you see increased polarization in charge-discharge if you did full cells?
Yes, so indeed, this dead lithium formation is a problem. So now, if I can remember correctly, we have used 50 micron thickness for the lithium metal, if I remember correctly. But it is not yet fully clear what happens inside the cell. So we have been able to make only small coin cells with the liquid crystals. And the conductivity value is still so low that we were not able to cycle them properly. So I'm hoping that we don't even see the dendrites forming there, since the liquid crystals should prevent the formation. So then, well, this remains to be seen, but I hope that we wouldn't have the dead lithium there that much, since it's indeed not what we want. And yeah, if we can just refresh or improve the contact between the electrolyte and the lithium anode, that would be hopefully the operating principle, but we are still not yet sure what really happens there.
Thank you very much for your answer. There are some more questions, but I think we can leave them maybe for the end for the round table discussion. So thank you, Maria, again. Maybe now we can proceed to the next speaker. So actually, now we will proceed with the paper-based techniques. And now I think, yeah, we have Joel, who is a battery development and process engineer at ABE. And he will be speaking about evaporation and sputtering processes for the deposition of lithium metal and its protective coating. So please, Joel, the floor is yours.
Thank you, Andrea.
You can put full screen.
Yeah.
Perfect. Thank you.
I'm going to share my screen. Okay, I wonder if you see my screen now. All right. Thank you, Andrea, for the very nice introduction. My name is Joel, like you said, and I oversee lithium metal solid-state battery R&D and process development at Avesta Battery and Energy Engineering. I'm representing the SPINMID project, And the aim of my presentation today is to discuss physical vapor deposition techniques, specifically evaporation and sputtering for the deposition of lithium metal and artificial SCI or its protective coatings. So let me begin with a word about the SPINLIT project. Essentially, the objective of the SPINLIT project is to develop practical and scalable lithium metal solid-state battery pilot plants based on digital manufacturing principles, such as digital twins. As you can see here, in addition to ABE, we have some of the most competent companies and research institutes working within the SPINLIT project. All right then, so let's just have a recap on why we are interested in physical vapor deposition processes for manufacturing lithium metal, right? So as discussed by, I think 2 presenters ago, it's shown that extrusion is almost the only process that is used to manufacture lithium metal foils. And because it's a very old process, it is industrially mature, and it has grown to the extent that you can have a very high throughput. The problem is that the nature of the process is such that because lithium is very reactive, it tends to lead to very high impurity in the manufactured foils. So in addition, the surface morphology of the lithium that's manufactured tends not to be very smooth. And like has been said, it's difficult to attain a thickness of around 20 micrometers that's required for lithium metal batteries. So typically the minimum that can be achieved is about 50 to 70 micrometers, depending on the manufacturer or the manufacturing process. And so because of this, it leads to low energy density of lithium metal batteries. Also, very importantly, we want the lithium metal to be laminated on copper foil, which is the current collector for lithium batteries. So it's almost impossible to laminate lithium foils produced by extrusion on copper foil. And so it has other disadvantages like high processing temperature, and it actually requires very, very high pressure in order to flatten the lithium. Physical vapor deposition processes, specifically sputtering and evaporation, actually solve most of these problems. It solves most of the demerits of manufacturing lithium metal foils. And because PVD processes have been used for 50, 60 years in the semiconductor industry, so it can potentially have a very high throughput. And the processes are such that you can actually obtain very high purity. You do not have the conditions of rolling that could contaminate the lithium in using PVD processes. And so you can actually control the thickness of the lithium, so you can get lithium as thin as a few nanometers to micrometers, however you like, and you can deposit on the copper current collector that you'd like for your batteries. The downside is that it is, at least for manufacturing lithium metal, it is a relatively new field, and so there is still a lot of work to be done in developing PVD processes for manufacturing lithium metal foils. And also, as stated earlier, it requires ultra high vacuum conditions, which could, increase the price a bit. All right then. So in this slide here, I just broadly differentiate between evaporation and sputtering, right? The first thing is that the deposition environment for evaporation is in a vacuum, right? And essentially what you do in evaporation is that you heat the source, the metal to be evaporated, and it vaporizes and then deposits on the substrate where you want to deposit the material. Meanwhile, in sputtering, what you do actually is that by the impact of electrons generated by negatively biasing the targets or the source in this case, you can actually have positive ions, typically argon gas, that impinge on the target. And so when this impingement occurs, then the material to be sputtered, of course, sputters out of the surface. It kind of lifts the surface and then it deposits on the substrate where you want it to be deposited. So it means that you have relatively higher pressure, right? Because you need the argon gas to generate the plasma in this case. So also, if you look at the sources, evaporation could be either from a melt, a liquid, or a solid phase, but sputtering is almost always from solid targets, and the energy required for evaporation is actually really, really low relative to argon, relative to sputtering, in which the argon have very high energy and then impinge or collide on the target that produces atoms of very high energy. Very importantly, the deposition rate of evaporation actually is just really a function of the equilibrium vapor pressure of the material at a specific temperature. And so because of this reason, you actually want to use as low pressure in the system as possible, which is why evaporation occurs in vacuum. Meanwhile, the rate of sputtering depends on factors such as the power that's used, the distance between the target and the substrate, also the pressure in the system. But very importantly for this conversation, something called the sputtering yield, which is a measure of the amount of atoms, that leaves the surface of the target relative to the amount of atoms that impinges on the target. The nature of the process is such that you can actually deposit any material, right, for sputtering. Meanwhile, for vacuum evaporation, you can only use pure elements. You can only use pure elements, and we are going to come back to the reason for this in the next slide. So evaporation, because it occurs in a vacuum, the purity of the deposited material is almost 100%, but sputtering, depending on the material, the process that's used, the working gas, it can have variable purity. All right, then let us look at the evaporation of lithium. So lithium is actually a very awesome material for evaporation, any kind of evaporation. The point is that lithium has a very low melting point, around 180 degrees Celsius, and it has a very high vapor pressure. So it means that at a relatively low temperature of 500 degrees Celsius, we can actually obtain the deposition rate of up to 400 nanometers per second. Right, and as you can see in the SEM images here, the morphology, both the surface morphology and the bulk morphology of evaporated lithium is very, very smooth. And so it means that depositing lithium metal on copper foil really is the way to go for manufacturing lithium metal batteries, whether in liquid electrolytes or in solid state batteries. The sputtering of lithium, on the other hand, is a bit tricky. And I think that in order for us to understand it, we really need to look at the properties of lithium. So as you've seen first, you see that lithium has a very low melting point of 180 degrees Celsius. And of course, it has a high vapor pressure, for this reason, at 500 degrees Celsius, right? Now, another additional thing is that because lithium is very reactive, any lithium that is obtained, any solid lithium that is obtained that will be used as a source for evaporation actually has a passivation layer, typically of oxides or carbonates, right? And this passivation layer actually avoids direct impingement of the ions on top of the lithium. And so because of this, actually, the lithium heats up when you try to sputter the lithium, right? Also, because deposition occurs in an environment containing another gas, typically argon is rarely ever pure. And so it means that there might be some other components of the working environments that could actually react with lithium. And so the result of lithium deposition by sputtering tends to be impure. Now, to understand this, let's look at the figure in the middle panel. When you try to sputter lithium, what you actually find, in opposition to what you would find in the sputtered deposition of other metals, is that when you begin sputtering, there is no deposition of lithium, but the temperature of the lithium itself begins to increase. And the reason is, as I've explained, that the lithium impinges on the passivation layer, which heats up the lithium that is below it. And so as you would see here, you see that once this happens, the lithium melts, right? But there's still no deposition. And as you continue until after about 800 seconds, then would you find that the lithium has begun to deposit. And at this point, it's almost 400 degrees Celsius, where the vapor pressure of lithium is very high, right? So this is really a different behavior from most metals that are sputter deposited, which actually shows or suggests, at least from the outset, that when you try to sputter deposit lithium, what you're actually doing is you are evaporating it. So in the last panel, the third panel, you'll find that actually from analysis of the deposition rates at different frequencies, it's been proven that at least 40% of the lithium that is deposited during sputtering, or that is supposedly sputter deposited, is actually by evaporation. And you would ask that, why does it matter, right? Well, it matters for two reasons. The first reason, as I've explained, is the fact that sputtering does not occur in vacuum. It occurs in the presence of other working gases. And these working gases are rarely ever pure, right? So it means that lithium is easily contaminated, right? The lithium that will be deposited is easily contaminated. But the second reason is actually a very more important reason, and it's what you see here is that when you do the energy balance, comparing the pure evaporation of lithium or the sputtering evaporation of lithium, you'll find that the energy balance, you'll find that the energy required for lithium deposition during sputtering is much higher than you would require for evaporation, right? So let's look at the energy balance, for instance. The total energy that you use to hit the substrate or do whatever, actually for lithium deposition is only has two components, which is the deposition energy, that is the useful energy that's used, and the second is due to radiative loss, right? Because which is just a function of temperature. The lithium metal is hot when you evaporate it, and some of the heat will be lost radiatively. But in sputtering deposition, on the other hand, there are actually four components. So in addition to the deposition of the useful energy, you have the radiative one, which is a function of temperature. So regardless of the process, the rate of energy loss during it's just a function of temperature, right? But in sputtering, you always cool down the target, right? And very, very importantly, there's a fourth component called the dissipated energy. And this dissipated energy, again, is due to the fact that when you sputter lithium not in the vacuum, but in the presence of a working gas. And so once the lithium atom is sputtered, as it moves through the reaction chamber, what happens is that it collides frequently with, in this case, the argon neutrals or argon positives. In any case, and this actually causes it to lose a lot of the energy, right? And so it's been found that actually the energy efficiency for sputter deposition of lithium is 10%, right? Meanwhile, we can actually conclude that the energy efficiency for evaporated lithium is 90%, more than 90%. This is a very, very important point because as battery engineers or as people who develop processes for manufacturing batteries, we have to, in order to be green, in order to be sustainable, we have to look at the energy efficiency or how much we maximize the use of the energy that we use in manufacturing our batteries. All right then. So finally, let's look at sputtering or evaporation for the deposition of lithium metal coatings. So what you see on the other hand, that evaporation is not a particularly useful method for depositing lithium coatings. And the reason is that lithium coatings tend to be multi-element ceramic materials. Now, we already know, right, that the coatings for lithium must be materials that are thermodynamically stable against the lithium metal. They must be electronically insulating ideally, and they should have reasonably high lithium ionic conductivity, right? And so the typical elements that satisfy these conditions are materials like lithium halide or lithium oxide or lithium nitride and the like. Now, if we consider the evaporation of this sort of materials, this compound materials or multi-element materials for the coatings, well, we see that we cannot deposit these compounds by evaporation. And there are two reasons for this, right? The first reason is that the partial pressure of most elements are very, very different. And by very, very different, I mean by difference of tens of orders of magnitude. And so it means that the deposition rate of each component of the compound will tend to be different, such that the stoichiometry of the deposit at the end of the deposition is really, really different than the stoichiometry of the source material. The second reason is that evaporation typically occurs from melt, and melts homogenize easily. And so it means that as one atom, for instance, is being evaporated faster than the other atoms, now the melt homogenizes, and so the composition of the melt changes. And so this is going to gradually change the composition of the deposit on the substrate. Now, sputtering, however, does not have the problem. As we've seen, the rate of sputtering is proportional to what is called the sputtering yield, like I've described. And actually, this value for most atoms is more or less the same thing. So it has a very, very narrow range between 0.01 and 4. And so it means that when you try to sputter from a target, the atoms actually leave the target at more or less the same rate, depositing, under the same conditions, having the same ratio on the substrate. Also, unlike in the case of evaporation, in which melts will be homogenized, sputtering is almost always from solid targets, right? These do not homogenize. And so it means that the composition of the target is the same throughout the deposition process. So this causes the composition of the deposits to be the same thing as the composition of the original source material, right? So it means that while evaporation is the better choice for the deposition of lithium metal foil, sputtering is actually the better choice for the deposition of protective coatings. Right, so I'm just going to conclude my presentation by showing the system we use here at ABE for the SPINMATE project, which really is a pilot line roll-to-roll process by which we evaporate the lithium. We use thermal evaporation of the lithium, and then we sputter the coating on top of the lithium. Thanks for your attention, and I'll take any questions if there are any.
Thank you very much. Checking the chat at the moment. I don't see any question at this stage. Thank you very much for the good explanation. Maybe if if the audience has some questions, we can go over those in the roundtable. So maybe now we can proceed to the next speaker. So actually, following in the topic of vapor-based techniques, we have now Ville, who is the head of technology and process development at Pulsion, and in particularly in the development of PLD processes and targets. So I think, yes, great. You're already here, so please go ahead.
Okay, thank you, Andrea, for the introduction. And hello, everyone. I will discuss here, as I previously mentioned, pulsed laser deposition of lithium metal and protective coatings, and representing the Pulse Lion project here, where we are building a battery composed of lithium metal anode with protective layers, sulfide-based solid electrolyte, and nickel-rich NMC cathode. And in Pulse Lion, pulsed laser deposition technology is developed into a single-step vacuum process where lithium metal and the protective layers, as well as the solid electrolyte, will be deposited in a single vacuum process without interruptions. So a multi-layer structure for the anode and the solid electrolyte layer. And here you can see the consortium full of expertise from around Europe. Pulsedeon is a company founded in 2018, so we've been around 5 years or so. We are concentrating on developing technologies for next generation batteries, especially lithium metal and lithium metal alloys, processing for anodes, the barriers and protective layers, as well as inorganic solid state electrolytes. We are currently participating in 3 EU programs, as well as 2 nationally funded Business Finland programs, where the pulsed laser deposition process for battery materials and various components is being developed. In addition, we do bilateral cooperation with industrial partners globally in EU, USA, and Asia. So I'll explain briefly the basic concepts of pulsed laser deposition and what makes the pulsed laser deposition process beneficial in producing lithium metal layers and the protective layers. It all starts with a target, so the source material for the deposition. A substrate is positioned so that the material which is ejected, removed from the target, can be collected and a coating layer can be formed. A laser beam, usually a pulsed laser beam, is focused on the target, and with the laser ablation action, material is released from the target. It proceeds roughly in a perpendicular manner from the target, of course, expanding into the vacuum space around it. Here it's written plasma. In ideal case of pulse laser deposition, it's plasma, but usually also consisting of various species. Solid particles can be also part of the ejected material, for example. And the plasma then travels from the target to the substrate and solidifies to form the coating layer. And all this, the process takes place in vacuum environment. Depending on the process and the materials, the vacuum level can vary. There can be reactive or passive background gases also present during the process. So what you saw there previously was a schematic presentation or the basic pulse laser deposition in 2 dimensions. But what we do in real life, we want to deposit on larger surface areas. So there are ways to deal with this to expand the deposited area. What we do is we scan the laser beam on the target surface to produce a kind of a line source of the material. Here you can see a real life image of the process in action, where a laser beam is scanned on a rectangular target, and material is being ejected towards the substrate, which sits above the target. So what makes pulse laser deposition attractive is that first of all, the adhesion of the material deposited on the substrate, the adhesion on the substrate is very good. For example, no lithophilic layer is required on the copper foil in case of producing lithium on copper. The process atmosphere is controlled, so we work in vacuum. As already mentioned in the previous presentations, the atmosphere with lithium metal is very important, and vacuum is one of the best to preserve then the purity of the lithium. We can deposit complex multi-element materials. Actually, pulse laser deposition is known for the ability to preserve the composition of the target material. In 80s, 90s, pulse laser deposition became known for production of high temperature superconducting materials like YbCO, a complex oxide, and there the stoichiometry was very important, as it is for some of the solid electrolyte materials for lithium batteries. Then, as mentioned, the multi-layer solutions. So in single process, all the different layers can be deposited without exposure to the environment, without harmful reactions taking place. And for example, there are publications on thin film batteries made with pulse laser deposition process, layer by layer. The layer thickness can be controlled. The thermal load can be very small. For example, we have been depositing materials on thin polymer separator membranes without damaging the separator membranes. They can be very sensitive on the thermal load. The porosity of the layers can be controlled from very dense to highly porous, and this can be advantageous for certain approaches on the current collector side, for example. And of course, various post-processing techniques can be used together with pulse laser deposition. Showing some tools of what we are using. So we have started with smaller pulse laser deposition systems, operating in batch and sheet-to-sheet operating modes. Now shifting towards the roll-to-roll processing, upscaling the processes. We have integrated glove boxes so that all the materials can be handled without contamination or exposure to the atmosphere. Roll-to-roll systems and systems with the capabilities to produce multi-layer structures. Here, for example, the S250 pulse laser deposition tool will be the one where to be used in the Pulse Lion project to produce the materials for the batteries and cells. It's completely a roll-to-roll system and capable of multi-layer deposition. What is important in the pulse laser deposition process are the targets used. So to control the process, you need to have high quality targets. In lithium, of course, high purity lithium. And when it comes to the protective layers, the solid electrolytes, controlling the composition is important. We are producing our targets ourselves, that thereby having control over the stoichiometry, the composition, the overall quality of the targets, and the temporal stability of the process. So we do lithium metal alloys, Lipon, LZO, and so forth. Some examples on the lithium produced on copper by pulse laser deposition: dense layers with good control of the thickness, nice smooth surfaces can be produced. Examples on the performance of the lithium on copper layers in previous LISA project, Horizon 2020 project. The performance was evaluated, and we saw that the performance of a 13 micrometers thick lithium layer is better than a 250 micrometer commercial lithium foil in this particular example. So they really work in a nice way. The adhesion is very good, as you can see that even bending and wrinkling and all kind of mishandling of the material, the lithium stays on the surface without any delamination. Upscaling has been done since, and we are moving now towards from coin cells to pouch cells and to roll-to-roll mode of deposition. Protective layers deposited on lithium. Here an example of a dense LZO layer on lithium. In this case, disc-shaped samples for coin cells going to be tested soon. So, as described, we have a scalable process platform providing temporal stability of the process, which is important when producing bigger amounts of material, then having good spatial uniformity, so thickness control over the whole substrate material. The process is monitored online and controlled based on the monitoring feedback. We have the targets we are producing ourselves, and all the materials being handled in a way that there's no contamination or harmful reactions taking place. All this will be upscaled then and can be upscaled into an industrial mode. This schematic showing how copper foil can be coated with a lithium metal layer and a protective layer in a single process with separate deposition chambers back to back, sequentially deposited. For example, 2 chambers for lithium metal and then a 3rd chamber for the protective layer. And for simplicity, now showing only the one-sided deposition. Of course, in real manufacturing, then the deposition would be on both sides of the copper foil. Again, summarizing the benefits. So the precise handling of lithium metal, lithium alloy anodes, multi-layer structures in one single process without exposure of the materials in between the deposition of the different layers, and having good control over the compositions and a continuous roll-to-roll process for the production. And what we are currently doing in the ongoing projects is the optimization of the interfaces, improving chemical and mechanical stability of the materials in operation in the cells, having good ionic conductivity of the protective layer. We will be doing post-processing solutions to further improve especially the quality and properties of the protective layers. And it's still an ongoing process also to fine-tune and optimize the targets used for producing the protective layers especially. So that's all I have to say at this point with and about pulsed laser deposition, and ready to answer any of your questions.
Thank you. So maybe we have time for a quick question. So here there is a question which says, which fluences are good for depositing lithium metal?
Yeah, well, there's no single answer to that, because of course you can use different type of pulsed lasers for the process. Typically nanosecond pulsed lasers are used, and then we talk about depending also on the repetition rate of the pulses, but in that case it's less than 5 joules per square centimeter, for example. Well, also depending on the wavelength used in the process. In pulsed deon, we use ultra short pulsed lasers, so picosecond pulsed lasers, and there again the fluence is a bit different, but yeah, it depends on especially on the laser type and properties.
Thank you very much for your answer. So I think maybe now we can proceed for the last presentation of the vapor-based techniques. So actually today we have here Sara. Sara, she's a postdoctoral researcher at Aalto University and actively conducting research in the field of electrochemical energy storage and conversion. And she will be having a talk today about ALD coatings to stabilize lithium. So
yes.
please, Sara.
Yes, hello everyone. Glad to be here in this scientific webinar. Can you see my screen?
Yes, we can.
Okay. Okay, today I'm going to give a discussion on ALD coating to stabilize lithium. Also, I would like first represent the Solid project, which is entitled Sustainable Manufacturing and Optimized Materials and Interfaces for Lithium Metal Batteries with Digital Quality Control. So the Solid project brings a group of research and industrial partners throughout the battery manufacturing. Multiple participants are involved in this project, which is aimed to scale up a high energy density and safe and easy recyclable solid-state lithium metal battery. As you can see, an overview of the work packages which is involved in this project, and each participants are responsible for different tasks and roles for instance, Aalto University and Pulsion and CSEM companies are responsible for developing a lithium metal anode processing technology and lithium metal foil surface engineering solutions. Aalto University focused on development and investigation of protective coatings for cathode and anodes using atomic layer deposition. The aim is to invent cost-effective and scalable approaches for avoiding active material aging and simultaneously improving their compatibility with other components. On the other hand, AB company responsible for manufacturing the pouch cells and evaluating the electrochemical reaction in the cells, and also assessing the safety of the cells. And the other also VTT company also provides pilot scale processing in extrusion, coating of NMC cathode layer with electrolyte and a slight die coating of solid state electrolyte. So in other companies like Armors also they are responsible for producing the coated current collector, especially designed for project applications. So in general, the aim of this project, by contribution of all these companies and research groups, is to manufacture solid-state lithium metal batteries to minimize amount of critical raw materials and improve the performance and safety of the battery. So in general, let's look at the current energy of today. The batteries are extremely important in our clean energy future, mainly through the electrification of transportation from switching from the combustion cars to battery electric cars, which can significantly reduce the greenhouse gas emissions. But the adoption of these electric cars are held back, which is mainly by the short range of the current electric cars, which is due to the low energy density of the modern lithium-ion batteries, which is used in these electric cars. So to address these issues, we need to develop a new high energy battery chemistry. But to understand how we can improve the battery energy density, we need to understand how these batteries work. So just briefly, you may know that the current lithium-ion batteries consist of the lithium source as an anode, as an cathode, which is all the lithium comes from the cathode, and is generally a lithium transition metal oxide, such as lithium cobalt oxide. And during the discharge, the lithium is all in cathode, and during the charging, the lithium moves through the electrolyte and insert itself into the graphite sheets where the anode is. So the lithium are stored between the sheets of graphite, and by moving these lithium ions back and forth between the cathode and the anode, electrical energy can be stored and released on demand. So now these modern lithium-ion batteries provide the energy density of about 250 watt-hour per kilogram, but by switching to anode material that can store more lithium, such as silicon or metallic lithium anode, we can further increase the energy density beyond 250, which is about 350 with silicon anode. And by moving beyond the lithium ions, we can access the energy density up to 450 watt-hour. So since the lithium metal has the highest theoretical capacity, which is about 3,800 milliampere-hour per gram, and consequently, it has been considered as an ideal anode for rechargeable batteries, such as lithium sulfur and lithium-air batteries, which these lithium batteries can provide a high energy, specific energy and exceptional efficiency, and also a longer lifespan for batteries. But however, there are still many issues that need to be addressed regarding to safety and cost of these lithium batteries. But in general, the main challenges in lithium batteries are instability of lithium metal and electrolyte interface, which lithium is highly reactive, and which can reactive with electrolyte and cause other side reactions. And also the formation of the dangerous dendrites on the lithium metal surface, which cause the use of lithium anode decrease in popularity. So unfortunately, lithium tends to precipitate as dendrites when it is used as an anode material during the charging. The formed dendrites would penetrate the separator and causing a short circuit. So, and also can cause gradually evolution of the dead lithium from dendrites, which can go further and increase the polarization and cause large volume change, which all can lead to fading the capacity of the cell. So to cope with these issues, many approaches has been proposed to make lithium metal anode viable in secondary batteries, including solid-state electrolyte, artificial solid electrolyte interface, structured anodes. But in Aalto University, our strategy is to develop the material and the processing technology for lithium batteries, which we are trying to improve the interfaces between the electrolyte and both negative and positive electrodes. So here we are trying to study and apply atomic layer deposition as a protective layer for both negative and positive electrode to improve the safety and stability of the lithium metal batteries. So we believe that it is believed that this preparation of the appropriate coating on the lithium metal can avoid the lithium dendrite formation and improve the stability of the battery. So just how the ALD works, atomic layer ALD is a modified chemical vapor deposition process in which the precursor react with the substrate in self-limiting half reactions, paused cyclically to build up a coating on atomic layer at a time. So in a simple way, the precursors can react first, pulsing and reacting with the substrate, and to purge away the side reaction, side products, and inert gas can purge, and then again pulsing the second precursor in order to react with the surface which is covered with the first precursor, and again purging away the side products by purging the inert gas. So in the result, we can have one monolayer of the material on substrate. So by repeating this cycle, we can optimize the thickness that is required. And so in general, ALD can conformally coat a wide range of the material with submonolayer precision of the film thickness due to the vapor phase precursors and self-limiting reactions. So we can precise control the thickness of the material on the substrate, and therefore can be used for improving the interfaces between the lithium and solid electrolyte or with a liquid electrolyte. So here, ALD is considered as an ideal strategy to enhance the battery lifetime due to its uniformity, high chemical stability, and no pinholes of the coating layer. So a considerable research work has been conducted on the use of ALD coating for modifying the lithium batteries material performance. Many ALD chemistry can be deposited at low temperature in an inert environment, allowing deposition on sensitive substrates such as lithium metal. But however, there are a few reports about the lithium electrode surface modification by using ALD, and due to high chemical reactivity and low melting point of the lithium metal. But the most material that has been studied for ALD coating on lithium metal is aluminum oxide, and beside there are other type of few reports and other materials that has been coated on lithium. But all the studies has reported that this ALD coating on lithium metal can improve the stability. For instance, the coating of the lithium phosphate on lithium has improved the stability of the lithium in the air atmosphere up to 6 hours, which can assure the safety of the lithium and therefore also maintain the capacity of the cell. And also in the solid state lithium batteries as well, the coating of materials such as aluminum layer, as an example here, improve the interfacial interlayers between the lithium and solid electrolytes, which has shown suppress the dendrite formation, which is reduce the overpotential compared with the bare lithium. So therefore, this reducing the overpotential and improving this contact between lithium and solid electrolyte maintain the stability of the cell and maintain the capacity compared with the bare lithium metal. So in general, lithium metal batteries have the potential to increase the energy density compared to the current lithium ion. However, we still have the safety concern on lithium anode, which is due to the high reaction of them. So the protective layers are one of the strategies which can enhance the safety concerns, which ALD is one of the ideal strategy to improve the battery lifetime because of its uniformity and high chemical stability. And at the end, I would like to introduce you our Electrochemical Energy Conversion Research Group at Aalto University School of Chemical Engineering, which is led by Professor Tanya Kallio, which we focus on development of the materials and devices for electrochemical energy conversion and storage. And thank you for your kind attention, and I'll be happy to answer any of your questions.
Thank you very much, Sarah, for the great presentation. Maybe one quick question before the break. So there is a question on how about the industrial production of these coatings with ALD? Wouldn't be prohibitively expensive? Can you comment on this?
Actually, we have some companies that are working on preparing the piloting this coating, but of course it can be, but still our scientists are working on designing this pilot slot die. But for our part, we are first is primarily testing to understand how this ALD work and if it is effective. But after that, of course, it's required to designing different ALD chamber in order to provide this coating to make it scale up. But there are some companies like Benek, which are designing different ALD reactors in order to scale up this. So of course it's possible, but it's still going on and requires some designing by other engineers.
Perfect. Thank you very much. So I think now we can proceed to have a 10-minute break, and we can be back in 10 minutes. So at 12. Hi everyone again. Hope you had time to get a coffee. I think let's move on into the next speaker. So actually we're moving away from the vapor deposition techniques, and we have here Milad. He's a principal researcher and a material specialist with a strong knowledge on lithium-ion battery. at Leitat, and he's representing the AM4BAT project. Milad, are you here to?
Yes, Andrea, I'm here. Thank you so much for your introduction. And thank you, Takwa, for inviting me. Do you see my screen?
Yes.
Yes. We need to full mute, full screen. Perfect.
Okay. Yeah. So yeah, here I'm going to talk about electrochemical lithium production from an anode-less battery. But since this work is a part of AM4BAT project, let me introduce the AM4BAT project, consortium, and the objectives it has. Already Timothée very well explained what the Horizon Europe is. So I'm not going to explain it more, but in general, AM4BAT is a 4-year European project under Cluster 5 that is working on the development of all solid-state anode-less batteries. And as you can see, there are 11 partners participating in this project. There are RTOs, universities, and industry partners from different parts of Europe. So here we can see the concept of the AM4BAT, the cell concept actually. So you see different partners are participating in the materials development, formulation, and also there is a printing step in this project, which includes the 3D printing of the solid state part, which is not related to this presentation. And we have the anode-free system in this concept, in this cell concept, and eventually there are 3 prototypes of cells which will be eventually produced by Leclanche in a multi-layer pouch cell. So as you can see, there are 9 work packages in this project. So I'm not going to talk about other work packages. So I will focus on work package 5, which is related to current collector tailoring for an anode-free battery. So I already know that most of you are experts in batteries, but to whom which are not familiar with the concept of anode-free, let me introduce you what the anode-free battery is. So in general, lithium metal batteries refer to use of pure metallic lithium as the anode material, which you can see in the middle. But the anode-less, which is also known as anode-free batteries, are different concepts aimed to minimize the use of lithium altogether inside the cell. So in an anode-less configuration, there is no lithium on the anode current collector before the battery's first charge. So, and during the first charge, the lithium deposits on the current collector, ideally in a reversible manner. So in another word, anode-less batteries are rechargeable lithium metal batteries with no excess lithium. So comparing the state of the art of the conventional lithium batteries with lithium metal and anode-free batteries, we can see that lithium metal and anode-free batteries could deliver much higher specific energy and energy density compared to conventional lithium-ion batteries. But we should consider that in this calculation or in this model, the additional weight of 3D materials or 3D structure of current collector or other additional weight which could be applied in lithium metal or anode-less batteries are not considered. So as you can see, in terms of specific energy, there is no big difference between lithium metal and anode-free configuration, which is due to the high specific capacity of lithium metal. But in terms of energy density, as you can see, the anode-free configuration, of course, if successfully developed, shows a higher value, which is caused by the low density of lithium metal, in fact. Considering the lifespan of anode-free batteries, since no excess lithium is supposed to be in the cell, A complete reversible stripping plating of lithium on current collector is required to achieve a high cycle life. So as you can see, the anode-less batteries has the poorest cycle life compared to the other two types. So let's have a closer look to the effect of reversibility of the stripping plating of lithium on the cycle life of lithium metal batteries in general. So as you can see in this plot, just before showing this result, I have to mention that this plot is obtained from a recently published paper by Professor James Tour and his co-workers at Rice University in Houston. And in this model, we should consider that in this model, NP ratio is defined as 1 plus excess lithium. So anode-free batteries have an NP ratio of 1 in this model. So as you can see, even with Coulombic efficiency of 99.9%, anode-less and lithium metal batteries lose 20% of their initial capacity in less than 300 cycles. Even we're using 100% excess lithium, which could be considered as NP ratio 2 in this model, the battery loses 20% of its capacity in less than 300 cycles. So in anode-less configuration, achieving such a high Coulombic efficiency is not easy at all. So in general, the deposition of lithium on the most of the current collector, including current, as you know, has a higher activation energy compared to lithium metal itself. So this high energy to be overcome leads to an ununiform lithium nucleation and growth on the surface, which eventually leads to lithium dendrites. Besides safety concerns related to lithium dendrites, in anode-less batteries, since the only lithium inventory of the cell is the cathode, I mean, it's stored in the cathode before charging step, and it's supposed that there is no excess lithium in the system, it directly affects the Coulombic efficiency. So how M4BAT is trying to solve this issue? As I said, M4BAT work package aims to address this problem, and 3 approaches will be considered to form a uniform and, let's say, controlled lithium deposition on the current collector. The first approach is coating the copper with elements such as silver and tin, which have relatively lower nucleation barrier compared to copper. So as you can see here, on the right hand, these are the last cycles of stripping plating of the current collector of pure copper and the current collector coated by silver. And as you can see, the current collector coated by silver has more reversible behavior. So, but these measurements are still ongoing, so we have to wait and measure exactly what the Coulombic efficiency in this case is. But it's clear that it's improving some stripping and plating of current collector. The second approach are the 3D hosts, which, for example, is zinc oxide doped carbon nanofibers. So this 3D host will be designed to help actually to protect the SEI layer from cracking from volume change during lithium deposition. And the third approach is an artificial SEI layer, which is made by a polymeric layer on the current collector. Since I'm not expert in polymer synthesis, I'm not able to explain what the synthesis model is, but this is what is already going on in this work package, and this work is done by CEA actually. So here, yes, since the project I mean, let's go back here. Yeah, the project is, as I told you, in the beginning of the second year. And the first year was spent mostly on materials design and synthesis. We are in the beginning of electrochemical evaluation step, and we have to wait either for approach number 1, 2, or 3 to see what is exactly of this modification on the Coulombic efficiency of the cell. So right now we don't have any result to prove that which approach is better than the other and if they are working in a good way or not. But since the aim of this webinar actually is to evaluate the processing and manufacturing of lithium metal batteries, I would like to show you one slide regarding the expected manufacturing cost for anode-less configuration. So this model is also developed by Professor Tour group using BatPack software, which can offer a bottom-up cost model approach using materials and processing data. These data is collected from different already published articles and some data gathered from the industry. So as you can see, it's not surprising that the anode-free configuration offers less final cost compared to lithium-ion batteries and also compared to lithium metal batteries. Since the labor, equipment, and land is expected to be lower in the coating line. So in AFB1, which is anode-free battery 1, this is the first sample they are studying on. In this one, the model is not considering the additional anode-related costs, such as 3D design or SCI artificial or other costs related to these manufacturing steps. So the cost of production could be decreased up to 20% if we consider AFB1. Even if some additional costs such as electrolyte and manufacturing are considered, which is AFB3 sample actually, is still 10% of cost is saved compared to lithium-ion batteries. So comparing the lithium anode-free batteries and lithium metal batteries cost, it's clear that increasing the MP ratio, which actually translates to thicker lithium film, can heavily affect the cost of production and, of course, energy density of the cell, as mentioned earlier. So in general, if anode-free batteries can successfully be developed, it's going to be a big step towards cost reduction and also increasing the energy and density of the lithium-ion batteries. So thank you so much. If you have any question.
Thank you, Milad. There is one question regarding the stripping plating. They are asking what current densities are being applied.
I think it's 0.2. Let me go back. If it's not written there, it's 0.2 to my knowledge. Sorry, not to mentioning it.
No problem. You can just maybe put it, write it down in the comment in the Q&A.
Yeah, sure.
Thank you. Okay, so thank you very much for your presentation. I think we can move now to our next speaker. So now we're going into the industrial scale production of lithium metal anodes. And we have here Gaetan. He's a lithium metallurgical engineer at the Innovation Research Department at Blue Solutions. And he's here representing the Sidwell project. So please.
So thank you for the introduction. So I'm Gaëtan Cabon. I'm an engineer in metallurgy in Blue Solutions, and I will replace for that talk one of my colleagues, Nour Daher, who is in charge in the company of the part of the Steel Belt European project. So today I have the opportunity to discuss with you about our industrial process in order to make thin lithium. So our process is based on the extrusion and lamination process. So I will make during that talk like an industrial point of view of the state of what we can do. But first of all, a few words about the Silver European project. That project aims at developing an all-solid-state lithium metal battery with a high performance and with in-situ hybrid electrolyte. So this should be done with a solvent-free extrusion lamination process, and that's why actually Blue Solutions is cooperating and participating in that specific project, because Blue Solutions is well known for its know-how of first the lithium metal, and secondly for the extrusion and lamination process. So some of this knowledge will be presented during that talk. But first of all, who we are. Briefly, Blue Solutions is based in France, Canada, and in California. And our production rate, annually speaking, is about 600 megawatt hours. We aim at developing, or let's say transforming, our Gen 3 batteries, which are actually launched for commercial vehicles, into our Gen 4 batteries, which should be launched until 2026 for passenger electrical vehicles market. So in order to do that, we have a very big, innovative mind, and more than 400 people are working for that development, composed of technicians, engineers, and researchers. And let's say, just to figure out how much innovation is important for Blue Solutions, we can say that more than 600 patents have already been published. Here, just a map to figure out where we are. So as I said, in the US, in California, and the headquarters in France, in Quimper. And we also just inaugurated different partnerships between our company and different universities in France. They are called LabComs. The first one has been inaugurated in Grenoble a few months ago, and the other one has been inaugurated in Nantes. What's about our strength now? So Blue Solutions is well known to be able to manufacture dry cathode. We can also elaborate our solid polymer electrolyte, which can be used in order to, for sure, resisting to turn white during cycling, especially due to the high module compared, for example, to liquid electrolyte. And then we can elaborate or fabricate our own batteries, and to monitor them when they are commercialized with our own services and softwares. But the main topic, of course, of this talk will be focused on the process of the lithium metal. So what's about our process? So first of all, we are collaborating and, let's say, actually buying our lithium ingots from different suppliers. And then we are using like an extruding machine like this scheme showed here, just for illustrating what I'm talking about. We are just putting the ingot in that chamber, making pressure on it, and via different specific and quite well controlled parameters of that die, we can make the lithium ingot going through the die, and we can have a very precise thickness of our extruded lithium foil. So this is for the first step. Then when we've gotten this kind of very precise thickness for the extruded lithium foil, we can go to the step 2, which can be performed, as you can see, at an industrial rate, let's say with a speed around 50 meters per minute. And we can, or it allowed us to perform more than 10 kilometers of laminated lithium foil, whose width is about 16 centimeter. And that process is quite well controlled, and it allowed us to decrease the thickness of the lithium at lower value than 30 microns. And we will see that we can go lower than 30 microns in the next slide. So then when this is done, we can stack every layers to each others and like create the batteries we want to commercialize. So I just introduced a bit our ambition, but our ambition is to move from our Gen 3 batteries into the Gen 4. I mean, we need actually to get thinner lithium metal for being sustainable and for a cost optimization, because as everybody knows here, the lithium cost increased drastically for the last years. And actually, it's a matter of being competitive to other industrial battery makers. So for us, it's a key point. We will see that we can do it. Then we need to optimize our polymer electrolytes that should be suited for a large range of operating temperatures. For example, we want to go from middle temperatures, let's say, to room temperature of use. And then our cathode, we can fulfill the conditions and the standard of the industrial partners for the active materials. So we can use an MC and LMFP. Here, I just wanted to show you a same image of what we can do for our cell with an 18 micron lithium laminated foil from production. So here in black, you can see our thin lithium. So I just presented before that we can go lower than 30 microns. So this is done, actually. We can, for example, achieve 18 microns quite easily. Then this lithium works on both sides, so there is no current collector. And in gray here, you can find a 14 or 15 micron electrolyte, and in white and gray, you have the active materials of the cathode. So that's quite good. And we can say that we've gotten a quite very thin lithium, considering the fact that it's made by rolling and considering the fact that it's actually working on both sides. So if we are looking at the cyclability of such lithium laminated foil, we can see that it performs a bit less than 600 cycles. So we already achieved more than the half of the fixed target with the industrial company we're working with. And if we are comparing that results, so the 18 micron lithium results with the 10 microns lithium results, we can see that we achieved 420 cycles in the same condition, of course. And that's quite good. And that's an important key parameter that has to be kept in mind. So, I mean, if we are decreasing, or even if we are decreasing the thickness of the lithium, it doesn't mean that the lifetime of the battery will decrease linearly with that thickness. So I mean, if we are optimizing our lithium, we can for sure achieve the full target fixed. But the way to make it happen, or in order to make happen the Gen 4, let's say, we need to achieve different points, different amelioration axes. So we need to make progress first on the bulk structures of our materials. For example, we need to go on our lithium studies, and we need to optimize the interfaces. Let's say the interface between the lithium and the electrolyte and the cathode. And we need to go further in our way of processing it. So thank you for your attention. And I also would like to thank Solid4B cluster to make that talk possible. So if you have any question.
Thank you so much, Gaetan, for this nice presentation. So
Welcome.
I think we have some questions for you. So I will take one and I will leave the rest for Timothy for the next session. So we have for the stripping plating, what are the current densities being applied?
Sorry.
Sorry. Yeah, this is not the last one. I think maybe it didn't upload.
Okay.
So
Do the cost calculation
the...
include the AG coating?
Not that one. Sorry.
No, it's not that
I
one
think maybe
either.
it's delayed.
Yes,
yeah,
I think
because
so.
it is 11 minutes. So yeah.
I think it's
Yes.
delayed.
So,
It's the last one. Yeah.
okay. So Andrea, go ahead with it.
Yeah. So yeah. How do you decide for the correct lithium thickness? The 18 micron performs better than the 10. What is the reason?
I cannot see this question. That's why it is not.
How do I decide? Actually, it's totally dependent on the lamination process. I cannot talk that much about it. It's actually our know-how, but let's say it's about very precise parameter for the rolling.
Okay. Thank you very much. I know it's tricky to how much you can share. Thank you. So I think maybe now we can give the word to Timothy.
Yeah. Just before that, we want to thank all the speakers for being here today and for the nice presentations and for the quality of your work. Thank you all. And yeah, again, we will give the floor to Timothy to moderate the last session. Yeah, feel free to pick the questions from the chat and interact with the speakers.
Yes, thank you. I've noted a few questions that came down throughout the webinar. I imagine every speaker is ready to open their mic and answer. So I will start simply, and I think this question can go through about all the speakers. On scaling up a reasonable light metal anode, which is the best production method in your point of view? So I see, Joel, you activate your cameras. Maybe start with you to answer this. So a question which came up in the chat.
Well, perhaps my response might be a bit biased, right? Because as I presented, I think that because of the precision, right, and the quality of the lithium metal that is produced, I believe that vapor techniques might be the most suitable for the production of lithium metal anodes, especially if you want the lithium metal anodes to, well, be laminated or bounded to a copper foil current collector, right? Other processes like extrusion or lamination, like has been discussed, it's difficult to have the lithium foil on the current collector, right? And the performance of batteries are better when it is on a metallic current collector. So in my opinion, I think that this is the better method.
Okay, thank you. Joaquin, if you want to have a go at this one, which method would you defend more?
Sure.
For scale, also for upscaling, because I
yes.
think also the question was reasonable upscale of such a method.
Yeah, I mean, as of today, I would say it's not totally clear. So following on what Joel said, he's right. So PVD techniques, evaporation in particular, as he presented, you can get very pure layers of lithium, and that's a key advantage. You can really well control the thickness of the layer, and you can go to really thin layers. So that those are key advantages, and you can go beyond the limits of other techniques like the current one, right? Extrusion and lamination. But well, progress is being made, as was shown in the last presentation, on the standard sort of processes as well, right? So the difference between different techniques is becoming narrower. And for the PVD, we would need to see if these benefits from the technical point of view can somehow justify the higher price, because there's gonna be a difference on the price, right? The drawback of these PVD techniques are the equipment that are required. So I wouldn't say it's clear the difference, but of course there are some benefits from the PVD that could be. And then electrode deposition could potentially be another technique which is in between, right? Maybe it could be easier potentially to scale up and be not that much difficult based off of the equipment that is required as the PVD, but at the same time you can get the quality of the lithium that you cannot achieve by the standard process. So there are different methods there that will be pushing to get the best trade-off between the quality of the lithium and the price, which is going to be a key factor as well.
Thank you very much, Jochen, for your answer. I don't know if anyone else wants to take up this question. Otherwise, I think I'll ask another one for time's sake. Okay, I was wondering myself, I was wondering what your opinion is on the time frame and what your projection is of when we will reach the economics of scale for lithium metal anodes production, and what you project in the future, and how fast or how slow we might reach this objective. Maybe Maria or Sarah, you can.
Maybe I could pass this question to Ville from Palsedon.
Yeah.
He might have a better answer.
So when would this be available? Well, for example, the pulse laser deposition, well, we expect 3 to 5 years, maybe.
3 to 5 years, okay. Anyone else has a concurring or objecting opinion? This. Okay, I will thank you, Ville. I will move on to another question. I was also wondering, how can your research and your findings in light metal anode production contribute to faster development of other generation 5 lithium-ion batteries, such as lithium sulfur or lithium air? Is there some connection that can be made between these generations and your research you're doing now? Sarah, if you have an element of response.
Yeah, I can give some comment on that. Actually, okay, they are the next generation of the lithium batteries. So we still have the issues that faced with the lithium batteries, lithium sulfur, lithium oxygen, lithium metal are quite similar. So if we can still, because the similarity in all of them, the anode material is lithium. So if we can still overcome these issues that we face with the lithium anodes. So first of all, then we can go forward and proceed further to go beyond the lithium-ion batteries. So as all we discussed today, so we need still to work on the scale of the production of the lithium and overcome this issues, which is related to the lithium metal and the highly reactivity of the lithium, because the lithium can provide a high energy density. But the other hand, the other issues are also faced with in the cathode side. For instance, in lithium sulfur, we have the shuttle effect or other problems, which is, of course, the other issues despite of the anode part. So, but each component of the battery is required to be fixed and find a strategy for each one of these components. So for now, first, the anode part is required to be overcome the issues, and then we can go forward for other overcome the other issues. So I think because the lithium is one of the effective way to improve the energy density, therefore we need first to overcome these problems to provide the safety of these lithium batteries, and then we can go forward and have a hope for the future to go beyond these lithium batteries.
Thank you very much, Sarah. Would anyone like to add anything on this? And otherwise, I don't know if we have time for one last question, Andrea, or if
maybe,
we should close now. Yes, please go ahead, Toby.
Yeah, yes, I was gonna mention that lithium sulfur, for instance, you mentioned, obviously there are the same problems with the lithium and some else that would need to be addressed, but I would highlight the key difference with the other cathode like NMC or currently being used cathode is that you don't have any lithium in the cathode when you assemble the cell, right? So the lithium would be the active material actually. So that's going to be a big difference between currently being developed lithium technologies and the generation 5, as you mentioned, right? Lithium sulfur, for instance. So that's going to be that's a big difference. The thickness of the lithium, the amount of lithium you need is different. So that's going to be a difference when developing the methods and so on for producing lithium metal anodes. Just to highlight that.
Thank you very much, Joaquin, for your complimentary comments, and thank you all for your answers. So, Andrea, I believe this will be the end of a roundtable then.
Perfect. Thank you very much for also the well timing. So I just want to conclude by actually asking you to give your feedback on the webinar. So you will have a pop-up, I think, on your on the Teams, and there are just 3 quick questions. It takes 1 minute to answer, and we are looking forward to your feedback to know how to proceed also for the next webinars and what would be of interest to you and how would you rate this webinar. So I don't know if you have it already. Did it already pop up? Yeah.
Okay, we can
we
see
would
the
very much
results
appreciate.
together, I think.
In the meanwhile, yeah, thank you very much all for being here, for all the presenters and the attendees, of course. And thank you to the European Commission for the funding to all the projects. I think I can say that in behalf of everyone here. I don't know, Takwa, if you would like to add some additional words.
No, actually, just I want to thank also our backup office, Innova, again, because they supported us for this webinar and they deserve to be thanked also. Thank you for all the projects. Thank you for everyone, and thank you for your time. I know that it is I mean, it's not easy to stay online for 2 hours and a half, but I think the quality of the presentations was so good to attract the attention of the audience. Thank you for the questions, and try to fill this pool, and so we can adjust a little bit on and make something much more better for the next time. This is all from my side. I think we can see a bit the interactions. Okay, 75%. It's good, I think. We are above the average, so.
Thank you very much. We will use this input to improve for the next one and take your suggestions on the topics.
Yeah, let's have a nice picture also for social media if you want. So, yeah, we need some smiles. Okay, done. Thank you all.
Thank you. Have a nice day.
You will see it on LinkedIn. Have a nice day. Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye, everyone.